In this example, we're going to be finding the matrix relative to a non-standard basis for the following linear transformation. We're going to let T be the transformation that takes us from R3 down into R2, and we're going to define that operation as T of xyz is equal to x minus y and y minus z for the two components. So the difference of the first two components and the difference of the second two components. We're going to let our two non-standard bases be basis B, which is 1, 1, 1, 1, 1, 0, and 0, 1, 1. And B prime is going to be 1, 1, and 2, 1. So basis B is for the domain, and basis B prime is for the codomain. We're going to find the image of a vector using these non-standard bases, where the vector in question is going to be 2, 4, 6. So the first thing that we're going to need to do is set up the matrix relative to the non-standard bases. So the idea is, what we're going to do to create this matrix is each column is going to be the image of one of our three basis vectors relative to our non-standard bases. So for purposes of what we're doing, we're going to refer to these three vectors as vector v1, v2, and v3, and then vector w1 and w2. So each of the columns in this matrix is going to be the image of one of our basis vectors relative to the non-standard basis b prime. So image of v2 relative to non-standard basis b prime, and the image of vector v3 relative to non-standard basis b prime. So let's go ahead and start by finding the image of all three of these vectors through our transformation. So T of v1 is going to be equal to T of 1, 1, 1. And again, this image is supposed to be the difference of the first two components and the difference of the second two components. So 1 minus 1 and 1 minus 1. Thankfully, we get the 0 vector, which I can set up really easy as a linear combination of these two basis vectors by saying it's 0 times 1, 1 plus 0 times 2, 1. As such, the first column is going to wind up being 0, 0. So the coordinate matrix of the image of v1 relative to basis b prime is going to be 0, 0 because of these two coordinates right here. Let's do the same thing for the next one. T of v2 is going to be equal to T of 1, 1, 0, which again, what we do is we take the difference of the first two components, 1 minus 1, and the difference of the second two components, 1 minus 0. What we wind up getting is 0, 1, which we are supposed to represent as a linear combination of the vectors 1, 1 and 2, 1. So the thing that I'd like to point out is that if I double the first vector and then subtract the second vector, we'll wind up with 0 and 1. So double the first vector and then subtract the second vector. If needed, of course, you could set up c1 times 1, 1 plus c2 times 2, 1 is equal to 0, 1 and solve that using a system of equations and a matrix. So the image of v2 relative to b prime is equal to these two coordinates, 2, negative 1. We'll do the same thing for the last vector. That'll be T of v3, our third basis vector, so 0, 1, 1. That is going to be equal to 0 minus 1 for the first component and 1 minus 1 for the second component. That'll be negative 1, 0. And again, we're supposed to be representing this as a linear combination of the basis vectors 1, 1 and 2, 1. So I'd like to point out the same thing as, no, I guess it's not the same thing as what we did. If I take the first vector and subtract the second vector, the two components will be 1 minus 2 and 1 minus 1, which is exactly what we're looking for here. So the coordinates I'm looking for would be one of these and negative one of these. As such, the image of vector v3 relative to basis b prime is the column matrix or coordinate matrix 1, negative 1. So these three columns will help us construct our matrix A relative to these non-standard bases. So this is going to be A is equal to the 2 by 3. First column is 0, 0. Second column is 2, negative 1. And the third column is 1, negative 1. Now that we have this matrix, we will need to represent our vector v, 2, 4, 6, as a linear combination of these three basis vectors. So what we'll point out for vector v is that v is equal to the vector 2, 4, 6. And we're going to set that up as a linear combination of 1, 1, 1, of 1, 1, 0, and of 0, 1, 1. Now again, if you wanted to call these C1, C2, and C3, set up a little system of equations. Actually, that's not a bad idea. Let's do that. So that's going to be C1 plus C2 plus 0C3. That'll be equal to 2. For the second component, that'll be C1 plus C2 plus C3 is equal to 4. And then C1 plus no C2 and then C3. That's going to be equal to 6. So if I take the second equation and I subtract the first equation, we'll get C3 is equal to 2. If I take the C3 equals 2 and plug it into the third equation, we'll get C1 is equal to 4. And if I take C1 equals 4 and plug it into the first equation, we'll get C2 is equal to negative 2. So that, relative to the basis B, means that we'll be dealing with 4, negative 2, 2, relative to the matrix B. So our next task is going to be to multiply A by this coordinate matrix, and that'll give us the image relative to the basis B prime. Let's see if we can continue this onto a second sheet. There we go. There's physics working for us. So we'll say next. We multiply. So we'll be taking A times that coordinate matrix of V relative to B. So that'll be the matrix 0, 2, 1, 0. Hang on, I feel like something got... Oh, no, nope, we're good. Negative 1, negative 1. We're going to multiply that by 4, negative 2, 2. So a little bit of poking and prodding is going to be necessary. So 0 times 4, 2 times negative 2, and 1 times 2. That'll give us negative 2. Then 0 times 4, negative 1 times negative 2, and negative 1 times positive 2. I believe that's going to be negative 2 and 0. So what this represents the image of vector v relative to the basis b prime. To get it relative to the standard basis, what we're going to do is take negative 2 times w1 plus 0 times w2. Those are the basis vectors from b prime. So the first basis vector from b prime was the vector 1, 1, and 0 times anything is just going to give us 0, so this will wind up being negative 2, negative 2. That would be the image of our given vector relative to these non-standard bases. Now, here is why what we just did is exceptionally stupid. Not a word I like to throw around. What we could have done is taken this vector, 2, 4, 6, and plugged it into this. 2, 4, 6. So we do the first component minus the second component, 2, negative 4, and we do the second component minus the third component. That's going to be 4 minus 6, and what we got is negative 2, negative 2, which by an amazing coincidence is the same thing that we got doing it the dumb way. I hope that you have fully embraced this problem making you not smarter.